Moving on to the characterization of fiber mats, looking more closely using a scanning electron microscope, results show thin bead-free fiber structures in randomly oriented formations. So the production of PLA fibers was obtained at 12%, which was also used as the basis for clay content. Varying concentrations of hydroxylated halcite were successfully electrospun into fiber mats. So I have included here images captured using camera lens. Let's zoom that in. Zooming in, when I peel this off the aluminum foil, you can see microfiber strands. This is for pure PLA only. And then for the PLA HHNT composite fiber mats, the fibers are not that observed and they have a much firmer structure compared to this one. And as you can see, they are not peeled off totally from the foil, maybe because of its thinness, or a plausible explanation would be because of the electric charge between the foil and the fiber mats, which keeps the fiber mats attached to the foil. Remember, this was initially a solution that has been electrically charged and traveled as a jet from the needle to the collector plate with the aluminum foil. Okay? Also, electrospinning this for about 4 hours or less only produces about 0.07 to 0.11 millimeter thick, which is considered very thin. Okay? So looking at the fiber diameter, as you can see, fiber diameters reported here are shown as a ranged value because the determination of each fiber's diameter was done manually, as there was no application software for automatic determination of the fiber's diameters of the SEM used in the methodology. But it was observed that increasing HHNT content slightly increases or decreases the mean average diameter of the composite fiber mats. Also, fiber morphology for pure PLA was observed to be smooth and densely packed. This may be due to the use of a conductive collector, which helped dissipate the charges and reduce the repulsion between fibers. On the other hand, the morphology of the polymer clay composite membranes was observed to have a slightly rougher, uneven surface with improved diameter uniformity. This may have been due to the increase in viscosity of the polymer solution, which affects the stream jet spin and results in increased fiber cohesion points. Incorporation of the clay in the polymer matrix has caused the fibers to have branching orientations, which may also affect the mechanical properties of the membrane. So next is the FTIR analysis of PLA and the composite fiber mats. So for the polymer matrix, characteristic peaks at 2995 and 2945 wave numbers can be attributed to a carbon-hydrogen bond stretch, while a strong peak captured at 1748 can be attributed to the carbonyl bond stretch of an ester. The intensity of the signal represents the strong dipole moment associated with the carbonyl of PLA. At increasing clay content, a broad signal was observed at around 3200, which indicates the presence of oxygen-hydrogen bonding. This in turn has affected the signal of the carbonyl bond stretch for PLA. The intensity of the carbon-oxygen double bond was observed to decrease at 1% HHNT and 3% HHNT, which may indicate a weakening of the dipole moment due to formation of OH bonding. It is suggested that the incorporation of a higher concentration of HHNTs affected the strong peak signals at 2995 and 2945 wave numbers originally detected in the PLA spectrum. A band shift was also observed for 1% and 3% PLA HHNT fiber composites at 626 and 632, which are associated with the formation of silicon-oxygen-aluminum bond stretch of halcite. So these findings could be attributed to the bonding interactions between PLA and HHNTs. So let's now investigate and evaluate the effect of HHNT to the mechanical property of the electrospun polymer matrix. So on the x-axis are the samples, pure PLA and 3 different concentrations of HHNT. In this first line graph, the sample with the highest tensile strength is at 1% HHNT, while the lowest is at 3% HHNT content. So this is the force. Tensile strength is the force applied over cross-sectional area of the material and is responsible for the stretching of the material. How long the material is stretched is also plotted here. Results show that pure PLA has the highest elongation and then it decreases with increasing HHNT content. What this means is that we go from an elastic material to a stiffer or less elastic material. And then the third graph is the stress-strain curve to measure the elastic modulus of the samples. So this graph shows which electrospun material has the best mechanical property among the fabricated samples, okay? So far, 0.5% and 1% HHNT content has the highest modulus. And then at 3% HHNT content, the electrospun fiber mat has low tensile strength and modulus. Also shown here, this may be due to the formation of clay agglomerates being a source of weak points resulting in reduced mechanical performance, as observed in other papers. So a wound dressing material needs sufficient tensile strength and elastic property to withstand stresses exerted by body parts, subject to distortion or movement, and able to contour to the topography of the wounded tissue. Hence, tensile strength and modulus can be connected to the conformability of the wound dressing material. The tensile strength and modulus of 1% HHNT content were observed to be the highest and most favorable reinforcement for the polymer matrix. Hence, the reinforcement of hydroxylated halcite slightly enhances tensile strength and modulus initially at 0.5% and 1%, and then diminishes as clay content decreases, as what's seen at 3% HHNT content. This can also be ascribed to the molecular interactions between HHNTs and the polymer matrix. The free hydroxyl groups on the surface of HNTs or the hydroxylated HNTs may not have been enough to be completely dispersed into the polymer matrix, resulting in increased rigidity of the composite fiber mass and poor mechanical property at higher HHNT content. Next is the surface wettability of electrospun fiber mats. So the average water contact angle was recorded. The electrospun PLA sample, known to be a hydrophobic synthetic polymer due to a lack of polar functional groups, exhibited a water contact angle of 110.6 degrees. The effect of increasing HHNT content on the polymer matrix resulted in a slight decrease in contact angle. However, since the measured contact angles for the electrospun fiber mats are greater than 90 degrees, the wettability of the mats indicates a hydrophobic surface. Although halcite was functionalized by alkali treatment to increase the density of hydroxyl groups on the external surface of HNTs, it has little contribution to the overall hydrophilicity of the polymer matrix. Increasing HHNT content in the polymer matrix may increase hydrophilicity, however, it causes the tensile strength of the composite mats to suffer. Water uptake of fluid absorption ability is a significant parameter for fiber membranes produced for wound dressing applications. Thus, the surface of the dressing contacting the wound must be hydrophilic to absorb wound exudates from scar tissues. However, it could be anticipated that having a hydrophobic property may be beneficial as an outer layer in contact with the environment to protect the wound from foreign liquids. So next is assessing the pore size of electrospun composite mats, which connects to the material's air permeability. In this characterization test, airflow at a certain pressure passes through the material soaked in a wetting liquid. The porosity of the fiber mats was measured and is presented here in Table 4. An increase of HHNT content revealed increasing pore sizes. Mean flow pore sizes of 3 to 6 micrometer may provide breathability at the wound site, allowing oxygen molecules to pass through the electrospun fiber mat. This may also increase cell viability and promote wound repair. Okay, as you can see here, at 1% HHNT content, it has the lowest mean pore size, and its smallest pore size is also 1.8 micrometers. The smaller the pore size, the better, so that it can also block harmful microorganisms from entering the wound bed. The average size of most bacteria, however, is between 0.2 and 2 micrometer in diameter. So for this material, PLA with 1% HHNT content, it is also only partially effective as a barrier to prevent microorganisms from entering the wound site. All right, so in conclusion, halcite nanotubes were treated with a mild alkaline solution to enhance the density of hydroxyl groups on the external surface of HNTs for better dispersion and interfacial interaction with the polymer matrix, and it was confirmed. 3 different concentrations of the treated HNTs were incorporated into PLA solutions and successfully electrospun. That said, the first objective of this study was successfully met. Then the conclusion for the second objective, which was to investigate and evaluate the potential of the electrospun composite fiber mats as a wound dressing material, are as follows. So the fiber morphology of the pure and composite fiber mats was good. So some images showed bead-free fiber structures in randomly oriented formations, which was also desired in many published papers. And FDIR results also revealed successful interfacial interaction between the hydroxylated clay and the polymer matrix. At 1% and 3% HHNT content, the chemical interactions were more evident compared to 0.5% HHNT content. Consequently, the reinforcement of low HHNT concentration, less than or equal to 1%, into the polymer matrix improved tensile strength and modulus compared with pristine or pure PLA. So we can say that the conformability is good at 1% HHNT content. However, increasing HHNT content further decreases the elasticity of the fiber mat, which may hinder the conformability of the material when applied to the wound surface subject to movement. Okay? As for the material surface wettability, its contact angle is more than 90 degrees, so the material is hydrophobic. So it does not address the absorbency property of a wound dressing. It was also concluded that the hydroxylation of the nanotubes has little significance to the overall wettability of the composite fiber mats. However, the waterproofness property of a dressing can be addressed if the fabricated material is used as an outer layer in contact with the environment, protecting the wound from foreign liquids. So it can be for waterproofness. Due to the porous nature of the e-spun material, it can allow air to pass through to give breathability to the wound surface. But it is still limited as it cannot absorb excess wound exudates, and it cannot totally block out all microorganisms due to its bigger pore sizes, or it can only partially block those microorganisms out. So although the fabricated PLA HHNT composite mats did not possess sufficient properties as a wound dressing, data shown here have significant importance that can aid to further tune the properties of fibrous biomaterials. Recommendations to further improve this study are as follows. It is recommended to use TEM or transmission electron microscope for a better observation of the employed modifications on halcite nanotubes. To help make the composite fiber mats more efficient as a wound dressing material, incorporating antibacterial agents into the polymer solution or designing a novel method of functionalizing the outer surface of HNTs with bioactive agents can be explored in the future. Although some researchers found that halcite nanotubes demonstrated no toxicity towards microbial cells, it is also recommended that additional tests for the biocompatibility of the PLA HHNT fiber mat should be made. The simplest would be in vitro analysis using SBF solution at 37 degrees Celsius for 7 days. Other advanced tests to determine the biological behavior of the composite fiber mats could also be utilized. So that ends my presentation. Thank you for listening, and God bless us all.